Hello. Today I'm presenting our CVPR 2024 paper, Multi-modality Scene Tokenization for Motion Prediction, called MoST from Waymo. Predicting the future behavior of other agents on the road is a core problem in self-driving. Many existing motion prediction models consume representations produced by perception systems, such as oriented 3D bounding boxes encoding the state of cars and pedestrians. These representations reduce input dimensionality, enabling the use of lightweight models. Intermediate representations like 3D bounding boxes are also easily rearranged and manipulated, making it possible to construct hypothetical scenarios for simulation and testing. But relying entirely on the outputs of perception models may result in more fragile behavior prediction. Perception models may fail to detect novel obstacles on the road that were not labeled during training. On the other hand, end-to-end self-driving models trained directly on raw camera or LiDAR readings might better handle the complexity of the real world. However, such approaches incur significant computational costs and lose out on interpretability along with modularity. In our work, we explore a hybrid system for behavior prediction, which combines the merits of both the end-to-end and modular paradigms. We train behavior prediction models which take in camera images and LiDAR point clouds, in addition to the perception outputs and map information used by modular approaches. Our primary contribution is a method of tokenizing multimodality self-driving scenes summarized here. To process raw sensor observations, we use large pre-trained image encoders to encode the 8 surrounding view camera images, which are then unprojected onto 3D points in the scene. We also encode bounding box and LiDAR point geometries with smaller, multi-layer perceptrons and pool all 3 types of features into a single token for each element in the scene. An important design consideration of MoST lies in the choice of image encoder, for which there are many options. We considered CLIP, Segment Anything, VQ-GAN, and Dino V2 as representatives of 4 different approaches to training large-scale image models. After encoding the camera images, we now have several 2D arrays of image features. We would like to associate these features with 3D points in the scene, such that they can be grouped and pooled according to object identity. To do so, we use camera and LiDAR calibration information to find the nearest camera image for each point, as well as the point's corresponding location in that image. We then bilinearly interpolate the encoded features of the nearest image to produce a feature vector for each 3D LiDAR point. In parallel, the 3D point cloud is decomposed into its constituent objects and regions, which are represented as 3D bounding boxes with headings. In addition to existing perception outputs, which identified road agents such as cars, bicyclists, and pedestrians, we also detect and divide the ground plane into a grid of 2D tiles. Finally, the remaining non-agent and non-ground points are clustered in each frame via a connected components algorithm and tracked between frames with a Kalman filter to produce unlabeled open set objects. We use the term scene element to refer to all 3 categories of objects and regions. The resulting per point image features and scene element bounding boxes are used to compute a feature vector for each scene element, which we will discuss next. To perform feature extraction for scene elements, first the per point image features are average pooled to yield 1 image feature vector for each scene element in each frame. We also encode coarse-grained bounding box and fine-grained point cloud geometry information with separate lightweight multi-layer perceptrons, which are then summed together to produce a geometry feature vector for each scene element in each frame. Finally, the geometry features and image features are summed together, along with a learned temporal embedding, and then processed with 2 self-attention layers. Our MoST model is based on the waveformer architecture, which uses a transformer encoder-decoder model to predict motion trajectories from tokenized road graph to traffic light, agent history, and pairwise agent interaction information drawn from maps and perception systems. After scene element feature extraction, MoST uses 1 additional token to represent each scene element, and these tokens are appended to the set of existing tokens and fed into the transformer encoder. Our model achieves a greater level of motion prediction accuracy compared to the original waveformer model, as trained and evaluated on the Waymo Open Motion Dataset. Shown here is a qualitative result illustrating a case where the use of raw sensor inputs enables our model to more accurately predict vehicle trajectories. The small red dots indicate the ground truth agent trajectory, and the large blue dots are the multiple predicted trajectories of each model. Compared to waveformer, our model correctly rules out the possibility of a U-turn, since it would lead to a collision with a portion of wall that is captured in the LiDAR and camera information, but absent in the agent and road representations used by waveformer. Our model is also able to make more accurate predictions in unmapped road regions, as shown in this example in which a car enters a plaza which is unmapped. None of waveformer's predictions capture the ground truth trajectory, but our model produces 2 trajectories that share significant overlap with the ground truth. Finally, we ran a series of experiments simulating road graph failures by dropping road segments uniformly at random from the MoST inputs. Even at a 30% failure rate, MoST exhibits similar accuracy to other recent baselines. Similarly, we were able to randomly drop up to 50% of road agents and maintain a comparable level of accuracy to our waveformer baseline. We look forward to further in-person discussion at CVPR. Our paper will be presented as poster number 37 in poster session 4. Thank you.